So, just to recap Thursday's lecture, I want to discuss with you for a few minutes two different inductive gauges to measure distance or displacement, and this will highlight the advantages of the gauges we discussed last week. So the first gauge will take the LVDT, and it has AC excitation, has two coils and some ferromagnetic slug which changes the coupling between this coil and either one of these coils. This is a part which we move direction X. The two coils are connected in opposite directions, so if this was A, this was B, we get here a voltage A minus B. Okay, and A minus B is very sensitive to the position of the slug, but it's quite insensitive to the non-measured quantities. And we said a good sensor has immunity to non-measured quantities. Non-measured quantities here would be, for example, sideways displacement, tilt. All these effects don't change the reading, just the exposition. So let's just compare this gauge for a minute to a much simpler gauge to measure displacement, which is actually also in use. You just take an inductor and you put a ferromagnetic piece here. So the lines of flux will couple through the ferromagnetic piece, and all what you do is you measure L. You measure L or you measure Z, which is the same thing, because as you recall, if this inductor has an inductance L, the Z, electrical impedance, would be 2 pi FL. Okay? Just to remind you, that is the impedance of an inductor, and if this was a capacitor, it would have been 1 over 2 pi FC. I'm assuming everybody remembers that from years ago. Okay, so let's compare these two measurement methods. As the piece of metal comes closer, obviously L will go up. The reason why L will go up, because there will be less resistance or less air gap for the flux lines to pass. Now this is even more clear if I actually put in here a piece of fixed ferromagnetic material. Let's say I put a piece of fixed ferromagnetic material here. So the only air gap is here. So all the flux is concentrated here at the poles, having to breach the air gap. Okay? Another reminder that L is defined in electrical engineering as N delta phi to delta I. In other words, what the definition of L is how much flux can a certain amount of current create. So, and we'll go back to this calculation in great detail when we talk about actuators, but just in a nutshell, if you decrease the resistance, there will be more flux, so L will go up. Okay? If you want to go one step further, flux in electromagnetic engineering is Ni divided by the magnetic reluctance, and the magnetic reluctance is equivalent of resistance. So this is like Ohm's law of magnetism. You don't have to worry about this right now, because all this, we'll go over it in detail in actuator. But this is just to illustrate the example that you can measure L, and L will change with this distance. And it also has some degree of immunity. For example, if this piece of steel moves this way, it would change the reading. Because only things which change the air gap will change the reading. So moving this way, rotation will not change the reading. So it has some immunity to non-measured quantities. Obviously, this is simpler than this. Okay? So now, all accurate gauges look like this, and this circuit is only used for very simple inductive proximity switches. You can see in some machines they don't want a switch with contacts, because the contacts will get dirty, the contacts can burn out, so they use some kind of solid state proximity switch. And this type of thing is used a lot in proximity switches. So you measure L, when L becomes too big, you know something is close, like to stop the machine. But it's not used really in linear accurate gauges. So this is used for switches, in other words, just on-off. This is used for gauges. So why is that? So let's start, see how awake you were last week. Okay, so let's just speak up. What's better? Why is this used for precision stuff and this is used for switches? Both measure position. Yes?
Differential.
And what is so good? This is differential, good answer. So what's so good about it? What's so important about it being differential? Okay, there's an answer at the back.
Differential measurements with noise.
Say it again.
You have a better noise rejection ratio.
Okay, so for one thing, better noise rejection. Okay, could you explain why the differential has better noise rejection? Wait, no, this all of you should know. So that's not your choice to answer or not. You have to know that. Okay, so why does differential have better noise rejection? Okay, so think about it. What happens if noise is added to both circuits? So let's say there is noise added to both circuits. Okay? So what? Wait. So what will happen to the noise in the differential? Well, you do A minus B, so both sides will have the noise. So here it will be A plus noise minus B plus noise, right? It will be A plus noise minus B plus noise, so the noise will cancel out. Okay? Good. So the first thing is, in the differential, the noise will cancel out. Now we're getting into trickier things. What other advantages does this have versus this? Yes?
Can you change it twofold? Like, creates a larger...
Okay, so that's actually, you started saying two things, but the second thing is accurate because you actually double the signal, because this moves this way. If this moves this way, A becomes bigger and B becomes smaller, so the difference creates a double signal. So it's not very important, but it's very true what you said. It doubles the sensitivity, doubles the signal, because if this moves by delta, this will be A plus delta minus B minus delta, so it will be A minus B plus 2 delta, right? So you double the signal, but that's not so important because you can amplify the rate. In a way, double the signal to noise, but that's not that important. But there is something more important that this allows us to do and this doesn't. So we already identified the first advantage. First advantage is noise reduction. But there is a second, as important advantage of differential versus single-ended. This is sometimes referred to as single-ended or non-differential. Okay, yes, please.
You're removing the constant. So if you have a constant, say,
correct, but it's a partial answer. If there is a constant offset or error in the coil, it gets removed. Okay, you already answered. Okay, let's hear some other answers. So what fundamental thing can we do here and we cannot do on the other one? Yes, please?
See the phasor direction, if you can see which side the plug is on?
Okay, that is true. If we do a phase-sensitive direction, we can measure, we know which side. But here we don't need it. Because here, if we pick some position as a 0, if we go closer, it goes up. If we go farther, it goes down. So we also know the direction. Okay? Now, there's something very, very fundamental, which is very important in any sensor, that we cannot do here and we can do here. Yes?
Input independent.
Pardon?
Is input independent.
And how do we do that? How do we do that?
To normalize.
Okay. So, this can be made input amplitude and parameter independent, not just input. For example, let's say the coils warm up. So as the coils warm up, the current changes because the resistance changes. Also, ferromagnetic properties change. This piece, which couples the magnetic field, if it warms up, it will change its mu. Mu is permeability. But here, we wouldn't know. If the output changed, let's say we have, okay, let's say the whole coil warms up. Because of that, things change. The magnetic permeability changes, okay? And in case we can measure L directly, that's the only thing which will affect it. If we're measuring current, to measure L. Many other things can change, because the resistance can change, everything can change, okay? But here, we can compensate for all the changes by normalizing, because what we do is we don't look at A minus B, we look actually at A minus B divided by A plus B. So any change which affects both sides will cancel out. So if, for example, the voltage changes by K, we said this will be Ka, Kb, K plus B, the K will cancel out. Okay? So if the resistance changes, the magnetic properties changes, the voltage changes, everything is cancelled out. That's called normalizing. So that is the key. Yes, please.
When you normalize, what happens to noise?
Pardon?
When you normalize, what happens to noise?
When you normalize, it doesn't help you with the noise, because in the case of the A plus B, the noise gets added. Okay? So it doesn't actually help you with the noise, because A minus B, the noise is cancelled, but on the A plus B, the noise is actually added. That's a bit complicated, because now it depends on the phase, whether it adds constructively or destructively, but in general, the normalizing does not help with noise. In fact, things are differential, help with noise. The normalizing doesn't help, because the noise only cancels out on the top, but noise is usually not such a problem. And let's see if somebody can guess. If this is AC driven at a frequency F, why is noise not such a problem? And that's a more subtle question, because we are going to talk about it a lot in the next session.
Filter for frequency?
Because you can put a filter which only allows the frequency F to come out, which is the frequency of the signal, and all the other frequencies of noise will not come through. Just like a cell phone or a radio picks one channel, one station, and the other stations don't come through. But there is a second subtlety to it, and we are going to get in next month into it. Can we really make a filter which is very, very narrow? It will only pass frequency F. Because this filter, F is very stable frequency. So in theory, one would say you can make a filter so narrow that no noise can pass. Because the noise, if this is frequency and this is amplitude, so that's called a spectrum. Okay, right? So the noise is typically appears at all frequencies. But the signal only appears at one frequency F, so it looks like we could make a very narrow filter which will never see the noise, but that's not true. And can somebody think about it, why that's not true? Because that's actually a very subtle question. And that goes back to Shannon's information theory. Yes?
The smaller your bandpass is, the longer you can sample?
Correct, but there is even a broader explanation, because, and we'll get into it in the next session of this course, Shannon proved in the beginning of, in the 1930s, that if you have a certain bandwidth, it can only carry a certain amount of information. So if you make this bandwidth very narrow, it can only carry a pure signal with no information, because as you move this gauge, the signal looks like this. Say you have a sine wave, and then you move the gauge, the sine wave becomes bigger, and then the sine wave becomes smaller. So what you get is a signal which looks very much like an AM radio station. This is called, in electrical engineering, an amplitude modulated signal, because the frequency is constant, and the amplitude is changing. So that's called an AM signal. So the output of such a gauge, or such a gauge, is what's called an AM signal. And an AM signal, if you look at its spectrum, carries not just a carrier, which is a sine wave, it carries sidebands. In other words, the information appears as other spectral lines. So the filter has to be broad enough to carry the information, not just of the carrier, but the sidebands. Now, I know most of you don't follow me right now, and I don't want to get too much into it, because we'll have a session on that separately. But just to give you an idea, when you look at AM stations on a radio, on an AM radio, they have to have some certain distance from each other. Although the filters can be made very narrow, but still typically there's like 20 kilohertz or 100 kilohertz between AM stations. And why is that? Why can't you pack them closer? Because when the AM station transmits music or speech, there are multiple frequencies, because when you take the Fourier transform of Z, and that's something you did learn, when you have this kind of waveform and you want to know the spectrum, you take the Fourier transform of it. And the Fourier transform of this actually looks like this, not like a single line. So in other words, that filter has to have enough bandwidth to carry the information created by changing of the position. When you change the position, the amplitude changes. These amplitude changes carry some information, just like an AM station. So you need such a bandwidth, so you can't get rid of all the noise. Now, this last 5 minutes, if you didn't understand, don't worry, because as I said, we have a special section next month about interfacing, and we go through all these considerations. So, bottom line, this is better than this for 2 reasons. We can reduce the noise and we can normalize. And the normalizing, and we can normalize, and the normalizing is very important because not only does it get rid of the changes in amplitude here, it gets rid of changes inside the sensor. Okay, and the last thing to summarize last week's lecture, I also mentioned that this is a thing shown in all the textbook, but it's actually hard to implement, especially if you want to do it right in the sensor, because it requires a division operation. And a division operation is very impractical. In analog, it's very difficult to do. It's possible, but difficult to do. In digital, it still takes some hardware to do a high-speed division, continuous division. So I mentioned there is a way that gets rid of the division. And how do you do that?
Feedback the A plus B to the...
Yeah, you basically keep A plus B constant. You force A plus B to be constant by taking another input, which is A plus B, and forcing this to change amplitude until A plus B is constant. Because if A plus B is constant, you are forcing the K to be 1, and then A minus B is out. And that's a much, much simpler way to deal with normalizing. Okay? So that's the summary of last lecture. Anybody who didn't understand all that, please raise their hand now, except for this part with the information contents, which we'll cover separately. Good. Okay. So now we are moving on to other sensors. So just to tell you a bit of what's coming, we are going to dwell mainly on position sensing. Now you can say, what about all other sensors? Because there's many variables you need to sense. Why are we spending so much time on position sensors? And the reason is that if you can sense position, you can sense a dozen other parameters by position. For example, if you can sense position, you can sense force. So if you have a cantilever, okay, and you put a force here, the cantilever will bend by force. So if you put a position sensor here, now you are sensing force. Okay? So sensing position and sensing force is the same. All that you need is a spring. Right? Because F equals Kx. If you can sense X, you can sense F. Okay? Now, if you can sense position, you can sense acceleration. Because now you can do this. You do the same cantilever, but you put a mass m. So if you accelerate, the thing will deflect. And this is a position sensor, P. So if you can sense position, you can sense acceleration, because F is ma. And we already know that if we can sense X, we can sense F. But if we can sense F, we can sense A. Okay? And of course, we can sense mass. If you just want to make a scale, if you want to make a position sensor, if A is just G, if it's gravitational, then you get a scale. Okay, so you have this, and you have an unknown mass. So when you just measure the deflection, you measure the mass. Just like a fish scale. A fish scale senses the position of the spring, but it actually measures weight. Okay? Is that clear? So basically, if you can sense the deflection of a spring, you can either sense acceleration if the mass is known, or you can sense the mass if the acceleration is known. Because the acceleration here is g. So here F is mg, but in this case g is known, so we are looking for m. Okay? Now, if you can sense position, you can sense pressure. All what you do is take a diaphragm. So I'm showing here a cross section. So this is a flexible diaphragm. So in top view, it looks like this. These ribs are put in usually for flexibility. Now you put a position sensor here, and you put the pressure here. Say that's a liquid. So now it will deflect from the pressure, and if you sense position, you can sense pressure. Okay? Okay, now a question. How many of those acceleration sensors does each one of you have? If you have to guess, if I ask you how many pressure sensors each one of you has, the answer is very little. Probably 1 or 0. Maybe you have a pressure sensor for your bike tires. But if I ask you how many accelerometers, this is an accelerometer, how many accelerometers does each one of you own? What's your guess? Somebody says 3. Not a bad guess for the average. The average person owns at least 3 accelerometers. First of all, if you own a car, you own 7. Because the airbags, every airbag has an accelerometer, and there are some other accelerometers. If you own a smartphone, you own at least 1. Because the way the smartphone knows to rotate your picture is by sensing the direction of G. Right? So if everybody owns a smartphone, you own at least 1. If you own some video games, you own 1 or 2 or 3, because in a lot of video game actuators have accelerometers. So the average student unknowingly owns 3 of those. And the average grown-up owns like 20. Start counting your house and computers and everything. So you own quite a lot of those. They are all built like that or like that sometimes, where there is a mass on a membrane. And the reason they are built sometimes like this or like this, because they are all micro-machined. Micro-machine means built from a monolithic piece of silicon, because all of those structures that I showed here are very suitable for micro-machining. For example, if I want to make a spring in micro-machining, I take the silicon and do some etching under it. So this is a silicon wafer, okay? Put some etching under it. Now, the position sensing here is not done magnetically, it's done capacitively, which I'm going to explain next. But the basic idea, you put in a position sensor here, and this is the cantilever which can bend. And if it's an accelerometer, you make the cantilever a bit heavier on top to have some mass. So this kind of structure is very, very good for micro-machining, making very low-cost accelerometers, where you can immediately put some amplifier on the same chip. So this is connected straight to the amplifier and normalizer. So the whole thing is one chip, which gives you a clean, large signal. However, when you take apart your accelerometer in your smartphone and other devices, you see that that position sensor is actually never inductive. It's always capacitive, which we are going to discuss next. But before we discuss it, can somebody make a guess why are all monolithic or micro-machine sensors, why are they all capacitive, sometimes different ideas, but never inductive? Yes?
Inductive, you have them coils, whereas
Yes.
capacitive are just 2 plates.
Right. So you can make coils monolithically, but you can only make limited number of turns. Because the way you make a coil monolithically, if this is a silicon, the way you make a coil, you make a planar coil. It's called a pancake coil. You lay out a thing like this, and here you make a via. A via is a passage through the silicon, and you have the return conductor underneath. Okay, so this is how you make coils in silicon. Well, this is metal. This is metallized conductor. But if you start calculating, you can have very limited inductance for two reasons. A, because you can only have one layer. B, inductance is limited to the dimensions, because it has to be fairly large to have high inductance, because when we go through the calculations of inductance later on, you'll see that you need a certain size to get a big flux and so on. So you can make coils monolithically, but they're all very low inductance. Performance is not so good. But in a capacitor, it's easier to make monolithically. You just deposit some metal on the silicon, and you have a capacitor. And because monolithic structures are very tiny, and the capacitance goes up as small as the gap is, in monolithic structures you can get reasonably high capacitance because the gaps are very small. And you can operate at very high frequencies, so you don't need much capacitance. So what you have to remember is that if you can measure displacement, you can measure a much wider range of parameters. That's not all the things you can measure. You can measure displacement. There's a long list of things you can measure, okay? And you tend to do it, when you make it small, you tend to do it capacitively, not inductively, just because capacitive sensors are ideal for very small movements and for micro machining, while inductive sensors are more suitable for mid-range movement, let's say from microns to millimeters, and capacitive sensors are suitable from millimeters to nanometers. So it's a different range. Okay? So now let's talk a little bit about capacitive sensors. The basic capacitive sensor is a plate capacitor where one plate is fixed and the other plate can move. Now, if these plates have area A, have a distance between them, which is what we want to measure, x, what would be the capacitance of such a plate capacitor? What's the formula for capacitance? You have area A. Okay, let's try somebody else. You have the answer today? Okay, so how about somebody from this side? What's the formula for capacitance of a plate capacitor?
K epsilon A.
Okay, started where? Say it again?
K epsilon A over D.
Very nice. Okay, good. So you should all remember that. C is epsilon, which actually is epsilon 0, epsilon r, and I explained those last lecture, times A over D. In this case, A over X. That's a formula of capacitance of a plate capacitor. Epsilon 0 is epsilon of free space. Epsilon r for air is 1. And unless you put the capacitor in deionized water, it's between 2 or 3 for other liquids. I mentioned before water has a high dielectric constant. Most water is contaminated by ions, so it will short out the capacitor anyway. But in theory, there is such a thing as deionized water. Water which has no ions, which is an insulator. Okay, you use it for cooling of electrical equipment. So if you put it in deionized water, then epsilon r can be quite high, but for most pipes we'll put it in oil, and this will be like maybe 2 to 3. Epsilon r will be 2 to 3. So, but 99% of the cases it's air. Okay? Now, so if we sense the capacitance, and there are meters which measure capacitance, we can measure the displacement. But there is something unpleasant about this formula. It is not linear. It's actually inverse. As x becomes smaller, the capacitance becomes higher, so you get a very strange calibration. You get a calibration, if this is c and this is x, you get a calibration, a hyperbolic calibration, which is very awkward, because at very small distances it goes to infinity. Okay? So the first trick in capacitive sensors is how can you make it linear? So can somebody think of it, when you look at this formula and you look at this device, what I would like to get is this actually. That's not C, but the position. I like to get something that's a position versus x, it's a straight line. So how do I get that while the capacitance behaves like this? Yes?
Impedance?
But okay. So the first thing, the easy thing is measure impedance. That's a good answer because I gave you before the formula that the impedance of a capacitor is 1 over 2 pi Fc. Okay. So if I plug it in, it's 1 over 2 pi F epsilon 0 epsilon RA divided by X. So X shows up here. So suddenly the impedance is linear with X. Okay? But so in practice, the way you do it, how do you measure impedance in a simple way? So you all know Ohm's law, which also works for AC, that V is IR, and if it's AC, it's I times Z. So the way you do it in AC, you run a constant current through this capacitor. So now the voltage you get is proportional to Z. So what you do is you run a current, I, through that capacitor, say this is ground, and you measure the voltage here. So the voltage here will be I times Z. Z is proportional to X. So, and here is a source, or actually this is a source. So if you run a current through it and the current is constant, you will get this. Is that clear to everybody? Because if the current is, if I is constant, the output voltage is I times Z, and Z is linearly proportional to X, which is what we're trying to measure. Okay? Now, in practice, you don't even bother with the current source, because if this voltage is small compared to the voltage available, you can just put a resistor here, and it will be practically constant current. So what people do, if you want to build a practical sensor, and you don't want to bother, a current source is not complicated, but if you want to build a quick and dirty sensor, what you do, you take your capacitive part, and you just put a big resistor and a voltage source, and as long as this is much larger than Z of the capacitor, the current will be this plus this. The voltage divided by this plus this, and if this is small compared to this, it will be roughly constant current, and this is enough to give you a linear output. Okay? But strictly speaking, you have to use a current source. So most sensors work over like 0 to 1 volt, and you usually have like 12 volts available in a circuit, 15 volts, so this is good enough. You don't need, if not, you put a proper current source from an op-amp. Okay. Now this sensor, of course, only works on AC, because in DC you can't measure the capacitance, it's an open circuit. But working on AC is actually an advantage, not a disadvantage. It's a big advantage of two reasons, and I will get into that more next month. Reason number one, you can put a filter. The way we discussed it here, or before, if you have AC of frequency F, you can put a bandpass filter which only allows frequencies around F to go through. So AC actually helps you, it reduces noise, and there is a much bigger advantage of working with AC, and that is, if you work with AC, you're getting rid of a big problem in low-level signals, and that is drifts. Because when you amplify DC, you have DC drifts. Every amplifier has some small voltage called an offset voltage, which drifts. But if you work with AC, all the DC drifts disappear. Now, DC drifts are a problem because when you work with very low-level signals, for example, just you connect two wires together, you can get a thermoelectric effect. So you have a nickel-plated post, a copper wire, you get a thermoelectric effect, and you can also get an electrochemical effect. So if you're working down to microvolts, it's actually very difficult to make a DC system which doesn't drift. But AC is no problem. It doesn't drift. Okay, that's the reason, for example, why telephones were designed from the beginning not to pass DC. Or that's the reason why audio amplifiers start at 20 Hertz, not at DC. It's much easier to design a system which only works with AC because you don't worry about DC drift. So the fact that the LVDT and the capacitive sensor only operate on AC is actually an advantage, not a disadvantage. Okay, so now let's plug in some numbers just to get an idea what are we talking about. So the capacitance of these things is quite small. If you actually plug in the numbers, if you have a square centimeter or a square, let's say a square millimeter for one of these accelerometers inside your iPhone or the car, okay, if you look at the micro machine accelerometer, A is a square millimeter, epsilon 0, I can't remember right now, it's something in the order of 10 to minus 12, that order I think. So now you're getting a millimeter is 10 to minus 6 in MKS unit. You're actually getting 10 to the minus 18 divided by, let's say, 10 to minus 6, it's 10 to minus 12, so it's about a picofarad. That's about right. If you take two little plates like this, the capacitance you get is about a picofarad. Now that's a very small capacitance. Like any wire or anything around it will have more capacitance than that. So this implies two things. You want to work at a very high frequency because you don't want to end up with a Z which is very high. And why is that? Because if you're working with a Z which is very high, let's say Z works out to be kilo ohms or mega ohms or giga ohms, any kind of leakage, any kind of dirt will short out the sensor. So let's plug in some numbers. This works out, if you plug in the numbers, this works about roughly 1 picofarad for a small 1 square millimeter sensor. Okay? So that's a very small number. You plug it in here, so epsilon, okay, so you plug in the numbers here, or you plug in simpler formula 1 over 2 pi fc. So you see right away, unless f is in the megahertz, you're going to get a very, very high Z. Because if this is 10 to minus 12, if f was 1 hertz, you're going to get 10 to the 11th ohms. 10 to the 11th is a huge resistance. Even if this is a kilohertz, you're going to get roughly here 10 to the 8th, which is 100 megohms. It's a lot. That means that any kind of dirt or moisture will short it out. So you really want to get down to kilo ohms to have a reliable sensor. That's a very good rule of design. If you work with kilo ohms, nothing bothers you. Moisture, dirt. If you work with mega ohms, everything bothers you. Okay, so you try to design circuits that the impedance is in the range of kilo ohms, not mega ohms, or sensors. Okay. I mean, you can design it for mega ohms, but then you have to pay attention to a lot of things. So in order to get this down to kilo ohms, if this is 10 to minus 12, okay, you really have to work here with 10 to the 11th, because that's 6, okay? Or work with smaller and smaller gaps, less than a micron. But in order, the general order of magnitude, F has to be many megahertz to bring Z down, let's say to 100 kilo ohm. Otherwise you end up with Z at many megohms. So, in a nutshell, all inductive sensors work in the kilohertz range, and the capacitive sensors work in the megahertz range. Now, the reason why inductive sensors work in the kilohertz range, because you don't need any more. You have enough coupling and it works well at kilohertz, why go to megahertz? But there's a second reason. The second reason is that when you make a coil which has to work at megahertz, it becomes difficult. Because a coil has self-capacitance. Any coil has some parasitic capacitance between the windings. So when you start making the coil for megahertz, it gets tricky. Okay, so it's much easier to build coils which work at kilohertz. On the other hand, it's much easier to make capacitors, which are very small and work at megahertz. So, as a nutshell, these things are designed usually very small, a millimeter, to make very small movements, microns, and they work at megahertz, but they work very, very well. And I'll give you a demo now in a minute how well they work. Now, the other thing is sometimes you want to sometimes you want to come from one direction and be shielded, so the actual sensor sometimes has some other arrangement. When you look at these sensors, they have not only just one moving plate, but usually you will see another plate. So if I look at one of these sensors from the front, I don't just see a round disc, which is this plate, I usually see a ring around it. And the ring around it is either used as a ground or as a thing called a guard, which we'll discuss again next month. Okay, so basically, because we're talking about a picofarad, it's very sensitive to anything near it. If I put my finger on it, my finger would add a picofarad right away. So if I just want to measure this and nothing else, I have to shield it somehow. So if I looked at this picture, what I would want to do, I would want to build some screen around it. So that screen will shield it from capacitance for other things. If this screen is grounded, then if I put some other object here, it will not see it. It will see a constant parasitic capacitance to the screen, but it will not see objects beyond the screen. Is that clear? Okay, so you have to do not just the plate, you have to minimally shield it and sometimes do something more sophisticated. Okay, so I'll pass around here one of these sensors and I'll give you a demo what it does. So if you look at the sensor, you see it has about a 2 millimeter disc, but it also has a ring around it, and the ring around it is a shield. Okay? So just look at it, there's nothing you can do except look at it. Pass it along. And now, okay, now let me set up a demo here. Okay, so I realize most of you will not be able to see the meter move, but you can see it on the video. At least the front several rows will be able to see the meter. So what I have here is a capacitive sensor. Okay. Come in front of it so I can see it with you. I have a capacitive sensor and I have a stage which can move very, very small movement. Now that stage, it's called a flexure design. That's a very good design if you want to move very, very small movement because it's all monolithic. It's all cut from one piece, so there's no backlash, there's no friction. Okay, and the way it's designed, there are some levers here which are monolithic, and there is a parallel motion stage which is monolithic. So, and when I turn the screw, the levers reduce the motion. So the screw is quite a precise micrometer. There's a set of levers that reduces the motion 15 to 1 or 10 to 1 roughly. And then there is a station here which can only move in a straight line. I wouldn't get into it. If you're really interested in these stages, I have some videos on YouTube about building instruments. So if you say Dan Gelbart prototypes on YouTube, pick the section called flexure. There's a section called flexure on YouTube, which if you have any problems falling asleep, just watch it. It's going to work for sure. Okay, this explains how this works, how this flexure works. For all what you care for now, this is a very, very fine adjustment stage where I can move things to nanometers. Okay? And I have a capacitance gauge, just like the one I passed along, plugged in at this end, measuring the stage movement. Okay? So right now, the capacitive gauge is set up that the full scale, okay, I have to let it stand because I don't want to flex it. Now the gauge is set up that the full scale is 1 micron. Okay? So I can easily move it. Oops, too much. And okay, I also see that I have to set it like this. Again. Okay, so I center it and I can move it easily left and right 1 micron. Okay, and it's a very smooth motion. There is no backlash because it's flexure. So if I turn back, there's no backlash. So that's why when you make very small measurements, it's much better to use flexure than things with slides and balls or lead screws because they have a backlash. Okay, so I can easily move it in micron. Now I can magnify the sensing. The air gap here, by the way, is 100 micron. So the gap between the plates of the capacitor is 100 micron, but I can easily move 1 micron. But what's interesting, I can set this stage to be full-scale quarter micron, which makes each division 10 nanometer. Now, 10 nanometer is pretty small already, right? 10 nanometer is already a big molecule, it's 10 nanometer. It's much bigger than a micro, okay? So I can easily go and move it very smoothly, plus minus 250 nanometer. Each small division is 10 nanometer. Now, it turns out that I could expand the scale to measure the movement of one atom. So the same thing, not made of aluminum, because aluminum is quite temperature sensitive, but if I made the same stage of quartz, so it's not temperature sensitive, using the same gauge and more gain, I can easily measure the movement of one atom. That's very surprising, that you can have such a simple thing and I can move it one atom at a time. Now people are confused by that, because they say, aren't the atoms jumping around? You know, how can you move in a stable way one atom? So it's true that all the atoms are jumping around, but over that area of a square millimeter, you are averaging zillions of them. So they're all jumping around, but the average position is very stable. And of course, it has to be a smooth, nice, smooth surface, which is easy. But with normal, everyday means, you can make a flexure stage and a capacitive gauge which can clearly see one atom at a time of motion, which surprises a lot of people. Okay? There are even tricks you can see thousands of one atom movement. But without any tricks, just by what I showed you here and by this, you can make a stage to see atomic movement. So what I can do, I can show you the sensitivity of this thing. I just zero it. And I have very nice control. You can see it's no backlash, I can zero it. Now I'll show you how sensitive it is. I'll just hold my hand next to it. Because it's aluminum, just the radiated heat from my hand is going to heat up this without touching. And it'll change it by many nanometers. So if I put my hand behind it, it will start drifting. See, I'm about a centimeter away, and it's drifting. It already drifted 50 nanometer. If you watch the meter, you'll see the meter drifting. I know you can't see the meter from the back, but you will see it on the video. Now it's already 60 nanometer drifted. 70. Now when I take my hand away, it's going to drift back very, very slowly. Okay? Now let's see who understands physics. Why does it drift back much slower than it warmed up?
The radiating body.
No, I can put a book, I can put this next to this wall and it still drift back much, much slower, like 10 times slower. See, it drifted up in a few seconds, it drifts down very, very slowly. Almost no drift back. Pardon? And can you explain why?
Because you're closer in your hands, much warmer than the air is colder than...
Okay, but in a summary, you are correct, but you can summarize much better. The rate of heat transfer, that's heat transfer by radiation, basically, because I'm not touching, right? So heat transfer by radiation is proportional to the force power of delta T. So delta T between my hand and this is 10 degrees C, okay? So I get 10 degrees C, but when I take my hand away, this only warmed up 100th of a degree from my hand. And the room is at the original temperature. So the rate of heat input is 10 to the power of 4. The rate of cooling is 0.01 to the power of 4. Right? So it's going to cool down 1,000,000 times slower than it heats up. Okay? Now if you don't understand that, you really shouldn't be in grad school. Because that's the first thing you learn about the heat transfer. Right? So think about it. So that's why it's very easy. If I actually touch it, it will heat up even faster. It do crazy things. It do crazy things because I deflect it. So it's very unstable. When I touch it, because it's both the effect of heat and maybe the effect of actually pushing it. Yeah. So some of the effect is pressure and some of the effect is heat. But it's interesting. Watch just moving my hand in and out without touching. I get 10 nanometer change just from doing this, from moving my hand in front of it. Okay? Just with the radiation. So obviously when you want to go down to nanometer measurements, you have to be very, very careful. You can't use aluminum. This was just a demo for students, but in real life, this would be from a material with zero expansion, like Invar. Invar is a metal with zero expansion, or zero dur. Zero dur is a glass ceramic with zero expansion, or quartz, okay, which is very good because this is cut on a water jet cutter, which you have, so you can cut it for quartz just as easy as for steel. So if it was a real life application, probably I would cut it out of zero dur or Pyrex. Pyrex is artificial quartz, like SiO2, but when people say fused silica or quartz are the same thing exactly. Quartz is the natural name for SiO2, fused silica, which are manufactured, not crystal. Pyrex is related to it. It's a glass with very low expansion, which is very cheap. But if fused silica is more expensive. But anyway, there's many materials with zero expansion. So if you want to do this for real, you don't use aluminum, but the sensor part, and that's what we are really all about. The sensor part is exactly like I drew there, operating at a megahertz or so, and very, very sensitive, can easily measure atomic dimensions. Okay, so the last part is this sensor has one problem. It's not differential. Because you can see if the current here will change, if something will change, I will get an error, and I wouldn't know is it drifting because the distance is drifting, or is it drifting because the current is drifting. So the question is, can one convert it to differential? And the answer is you can, and you can quite easily. There are several ways to make a capacitive sensor differential. Most people don't bother, because most people in the use of these capacitive sensors, a lot of the times you're interested just in short-term measurement. So, like now, I don't care if tomorrow it will be a different value. I just wanted to see the movement. Okay? So a lot of the commercial, I think any commercial capacitive sensor I've ever seen was not differential. But if you need a differential, you can make a differential. And I'll show you how. Okay, what you do is, let's say you had 2 plates instead of 1 at a distance L, and then you had a moving plate here, and this is a moving plate, and let's say this distance is X, and this is L minus X. So I'm ignoring the thickness of this plate, but this can be made a bit more than that. Right? Just for making it simple, this is X, this is L minus X. So when I move this plate, and let's say this plate is grounded, and these two are driven. These two are driven by constant current sources. Okay. This is grounded. So now when I look at this voltage, let's call this A, call this B, and I'm looking at the voltages A and B. Okay, so obviously when I move this plate, this voltage here will go down, this capacitor is going up, and this voltage will go up. Okay? So if I do a calculation, I know already from before that Z is this, okay, and I know already from before that the position of the voltage is I times Z. So I know that X is going to be I times Z. So this is I. And I already did the calculation. It will be, X position will be IX. I'm just copying it from here. 2 pi F epsilon 0 epsilon R times A. Okay? So to make life simpler, let's call this whole thing K, because that will repeat in all the equations. So this will be Kx. Now, I also, so this will be this side, so this will be VA. So this is the same, let's not call it X, let's call it VA. The voltage side A. So by the same logic, VB is going to be the same thing, but instead of x, it will be L minus x. Because the same thing applies to this side, so this will be K times L minus x. Is that clear to everybody? I just skipped to doing the calculation again. So, I can see from here, I can normalize it. For example, if I do, what I want to do is I want to get rid of K, because K has all the things which can change. Like epsilon can change, the frequency can change, the amplitude can change. So all the things we can change are lumped into the K. So if I do VA divided by VA plus VB, okay? I will get Kx divided by Kx plus Kl minus x. Okay? So now K will cancel out. Okay? K will cancel out. That's what I want to get. And then I'll get it's equal x over L. Because x will also cancel out. Okay? It's very simple. In one step, I made a differential. So I'm getting the output, the displacement, equals x over L, and L is a constant, so it's completely linear with x. It doesn't depend on frequency, doesn't depend on current, doesn't depend on epsilon. Everything cancels out. Everybody follow? Good. So this is actually a very elegant way to make a capacitive sensor. However, I mentioned before, I've never seen it done. All the capacitive sensors are the type I cast around. Now, can somebody guess why? And I'll give you a hint. A capacitive sensor in, say, in labs, in mechanical engineering, has a huge advantage over an inductive sensor. And if you do that, you may lose some of the advantage. That's a hint. Okay, so let's start with the advantage. What advantage does a capacitive sensor, in practical terms, not in theory, but in practical terms, what advantage does a capacitive sensor have over inductive? Come on.
Non-contact?
Pardon?
Non-contact?
Beautiful. That was very good. Okay? Because an inductive sensor has to touch the object it's measuring. So let's say you want to measure run out of a shaft. So the inductive sensor has to touch the shaft is turning, the sensor is bumping, and it can wear out. So there is some limit how fast and how rough you can measure. But a capacitive sensor doesn't have to touch what it's measuring, and since most machinery is grounded anyway, so if you had a motor, okay, or if you had, say, a lathe, you had a lathe with a chuck, and you had a workpiece with a chuck, this is the lathe, and you wanted to measure the run out of this workpiece. If you put a capacitive sensor here, you can spin the lathe as fast as you want, it doesn't have to touch. Okay, but if you want to make it differential, the grounded piece has to come between these two plates. It's a little bit more difficult to set up. If I wanted to make it differential, I would have to put another plate here. So that is a little bit difficult to set up because I have to adjust the gap that it's centered. So because of this inconvenience, people say, I wouldn't worry about the drift, and I'm using it for a short-term measurement anyway. But if you wanted a long-term measurement and you wanted to build it into the lathe immune to drift, it's better to do that, differential. But for most measurement, you only do that from one side because then it works like a dial gauge. You bring it like a dial gauge, hold it there for a second, measure, and that's it. So, the main advantage of capacitive gauge is a non-contact gauge. Now, the fact it works at a very high frequency, I mentioned that F is many megahertz typically. It can go to a gigahertz if you want. The fact it works at a very high frequency also means that it can measure very fast deflections, while an inductive sensor cannot. And now we have to go back a little bit into electrical theory. Why is there a relationship between the frequencies the gauge works at and the speed in which it can measure things? Okay. So, I mentioned before that the signal coming out of these gauges looks very much like the signal that your AM radio picks up. In an AM radio, you have a carrier, and the amplitude of the carrier is modulated, in this case, by the music. So this basic sine wave, that's called the carrier frequency. Okay? Sometimes referred to as CW, continuous wave. Now this is a modulation. This is the envelope. I mean, this line doesn't really exist. I'm just drawing the envelope. Okay, so if you connect it at the oscilloscope to an antenna to your AM radio, you'll see this. If you connect it to a AC gauge, you'll see the same. If I connect the scope to an LVDT and I'm moving the LVDT, or if I'm connecting the scope here and I'm moving the plate, I would see the amplitude being modulated. Okay? Now, what happens if I move it faster and faster? If I start moving it faster and faster, the envelope will start getting modulated faster and faster. But at some point, there aren't enough sine waves inside to make an envelope. Let's say if I move it faster than the carrier. If I move it faster than the carrier, what will come out is just noise. Okay? So this gives you an intuitive feel. I can show you the math too, but the math is less important than the intuitive feel. The intuitive feel says that if you have a carrier, you cannot have an envelope faster than the carrier. You don't even want to come close to the speed of the carrier. Now the envelope is the speed you're moving the gauge. The carrier is the frequency the gauge operates on. Okay? So, if you want to measure, say, high frequency vibration, you have some structure, it can vibrate to many kilohertz, your carrier should be in the hundreds of kilohertz. Okay, if you're dealing with little structures like piezo, micro machine, the natural frequency of these little structures could be 10, 20, or 100 kilohertz. Like a piezo could easily be 100 kilohertz. So you want the carrier to be megahertz. So because of that, a capacitive gauge, which is non-contact and operates at a very high frequency, is very suitable to measure very high-speed displacement. Because when you measure high-speed displacement, you don't want to touch the object, because it will shake and wear, and you want a very high carrier, so no matter how fast the object moves, the carrier is still much faster than the envelope. Okay? Now, for those of you who are a little bit more math inclined, what all this means in mathematical language, if I draw a spectrum, and this is amplitude and this is frequency, the carrier looks like a single line. If I just had carrier with a single frequency, the envelope, if the envelope was a sine wave, let's say if the envelope was a pure sine wave, and this was, the carrier would be F, and the envelope would be Fm, standing for modulating frequency, the spectrum would look like this. It will have, depends on the depth of modulation, of course, because it depends if the modulation is shallow or the modulation is deep. But let's say the modulation is full depth, it will look like this, and this distance, this will be Fc, or F, and this will be F minus Fm, and this will be F plus Fm, and these are the three spectral lines. Now, if you slow down the motion, Fm becomes slower, so these come in. So this is for a slow modulation. As you move the sensor faster, the F modulation becomes higher, since this distance is Fn, these sidebands move out. And that's how it ties to what I said before, that you need a certain bandwidth to pass the information. Okay? That's exactly a theory of AM radio. Okay? So I don't know how many of you have some background in signal processing, but that for those of you who do, that should make sense. Okay? Good. As you know, if you transmit a signal, there's another way to transmit a signal, and that's by frequency modulation. Instead of modulating the amplitude, you can do another trick. You can make this capacitor part of a circuit, like an oscillator, and changing the capacitor will actually change the frequency. Imagine if instead of doing this, I do something very different. I take this capacitor in a capacitive sensor, and I put it in parallel to a coil, so I get a resonant circuit. Okay? So this resonates, okay? Okay? So this has a resonant frequency. Now if the capacitance changes, the resonant frequency changes. So what I get here a signal which has constant amplitude, but the frequency changes. If you look like this, as I bring it closer, the frequency will become slower, because C becomes bigger, the frequency will become lower. Okay? So this is an FM output, just like FM radio works, and this is an AM output, just like AM radio works. Almost all sensors are AM, but there is some subtle advantage. So you're actually doing a frequency modulated sensor, and it has the same subtle advantage as AM radio has over, same subtle advantage as FM radio has over AM radio. So does somebody know what is the advantage of FM radio over AM radio?
You have stations closer together.
Pardon?
You have stations closer together.
In AM.
And
No, the other way actually. AM is much closer than FM. Because FM spectrum is actually wider. FM spectrum looks like this. It's a Bessel function. So actually it takes up more spectrum. But anyway, still a reason to do it. It takes up more spectrum, but there's a reason to do it, yes.
The frequency modulated has a constant amplitude. So
And what's so good about
higher
that?
power.
Pardon?
You can have a higher constant power.
It turns out that's not the main advantage. It's true. What you say is completely true. This has constant power, but has constant amplitude. It's nicer for the amplifiers. They always run at full power. But that's not the reason why FM was used or invented. Yes?
Gain doesn't matter?
Pardon?
Does gain not matter?
Gain is less sensitive to gain, but all AM radios have what's called an AGC, automatic gain control. It's a simple normalizing circuit which takes out the gain, which works like the normalizing circuit. No, there is a fundamental difference between AM and FM, and that is the reason why AM radio won over FM. You can listen to the difference yourself in your radio.
Better quality sound.
Pardon?
Better quality sound.
Not just that, it's related, but there is a huge difference between AM radio and FM radio, and it's the same difference applies to sensors if you run them FM or AM. The difference is noise immunity. The reason FM was invented, it has a much higher noise immunity, because if you would have noise on AM, I mean, I don't want to get into the theory of it because I can see that you don't have the signal processing background, but in a nutshell, if you have spikes of noise here sitting on the FM, these spikes of noise would only matter if they appear near the zero crossing, because the FM detector just looks at frequency. It doesn't care if the amplitude jumps, it doesn't care if the waveform is distorted. All what it cares, it counts zero crossings. Okay? So unless the noise is bigger than the signal, it's not going to affect the count of the zero crossings much. Okay? So because of that, the FM radio has at least a tenfold improved noise immunity, and the simplest test to do it, just turn on a vacuum cleaner or a mixer or an electric hand drill. Basically, turn on anything which has a commutator which makes sparks, which makes electrical interference. Take your AM radio, switch it between AM and FM when an electric drill is running next to the radio. So on the AM radio, you'll hear a noise at the frequency of the drill. You'll hear superimposed on the music. You switch to FM, this noise disappears. And that was why FM radio was introduced. Who invented FM radio? Okay, that's Armstrong. And it's a sad story actually, because RCA was dominating the radio business at the time, was interested in introducing television, so they didn't want to divert the public attention to the FM radio, so they refused to introduce FM radio. So Armstrong jumped out of the window of a hotel and died because of that. So it ended up a sad story, but it's a great invention. Okay, so anyway, so most sensors in AC still use AM modulation because it's simpler, but if you have an extreme case of noise, you can make an AC sensor based on FM, and then it will work like an FM radio. We'll have about 10 times the noise in unit. But it's very rarely done when you need it. Okay, see you on Thursday. So this is a typical capacitive sensor. The golden circle in the middle is the actual sensing electrode. The ring around it is a guard or a shield, and what it does, it protects the middle electrode from the effect of objects, because the capacitance of this electrode is so small that if it wasn't shielded properly, any placing of an object behind it will affect the capacitance. So you have to shield it, and sometimes you use a guarding technique and a shielding technique to make sure it only sees the capacitance in the front and it's shielded or isolated from anything at the back. Now this is a flexure stage, which is good to demonstrate small movements. So this is all a monolithic flexure stage with levers to demagnify the motion, and then a parallel motion stage. Now this is just for a tutorial for students, so it's made of aluminum, but aluminum of course is not stable enough in temperature and time and so on for really high precision stuff, but for a demo it's good enough. So the capacitance gauge is plugged at this end, measuring the movement of this block. Now you can see a few things right away. This is 1 micron full scale. This is +1 micron, -1 micron. You can see I can move it very smoothly without any backlash over a 1 micron range. Right now the air gap here is 100 micron, and I can move from 0 to 200 micron. Now I can increase the gain until a minor division will be 10 nanometers. So right now I'm at a 250 nanometer full scale, and each minor division is 10 nanometers. And again, I still have a very smooth motion, no backlash. However, now the limitations of the aluminum will come in. For example, if I hold my hand above the gauge without touching, it will start drifting, and the reason it's drifting is just from the radiated heat from my hand. Okay. So you can see that this is not so good if it's made of aluminum for high precision measurements, but in real life this piece will be made from Invar if you want metal, from Zero Dur, which is a glass ceramic, from quartz or fused silica if you want it in glass, or any other material with a near zero temperature coefficient.